Friends, today we will study the dynamic modeling of hydro turbines and hydro governors. We have studied the dynamic models for steam turbines and turbo governors. The characteristic of the hydraulic turbine are different from that of a steam turbine, and therefore, different dynamic models are required for hydro turbines. The physical arrangement for a hydro power plant is shown in this diagram. This is the hydro turbine. This is the water storage tank, we will call it 4-bay, and this is the penstock through which the water flows from storage tank to the hydro turbine. The tangent characteristic of the hydro turbine is determined by the dynamics of water flow in the penstock, and we shall determine the transfer function of the hydro turbine. Now, when we consider small perturbations about a steady state operating condition, then we can relate the various parameters by linear equations. Now, this equation, that is Q equal to A11H plus A12N plus A13G, and another equation M equal to A21H plus A22N plus A23G. Now, these two are the algebraic equations. In this equation, Q stands for per unit deviation in flow, H stands for per unit deviation in head, N is per unit deviation in speed, G is the per unit deviation in gate position, M is the per unit deviation in torque. Now, we can say here that for small perturbations we can relate the per unit deviation in flow to per unit deviation in head, per unit deviation in speed, per unit deviation in gate position. Similarly, the per unit deviation in torque is related to per unit deviation in head, per unit deviation in N, that is the speed, and per unit deviation in gate position. Now, these are the two algebraic equations which relate the small change in the water flow following change in head, speed and gate position. Similarly, this is the change in torque produced following the small changes in head, speed and gate. Now, using these equations and using the dynamics of the water flow in the penstock, a transfer function model for the hydro turbine is obtained. The transfer function relating the mechanical power output of the hydro turbine to the gate position or position of the gates, that is PGV is the position of the gates, is related by these constants which were shown in those algebraic equations and an important term TW. Now, this TW is the water time constant or water starting time constant of the hydro turbine. We will discuss about this time constant TW in detail. Further, these coefficients A11, A12, A13, A21, A22, A23, these can be interpreted as the partial derivatives of Q with respect to head, partial derivative of Q with respect to speed deviation, and so on. Now, for an ideal turbine, which is normally considered to be a lossless turbine, the N for rated speed, ideal turbine at rated speed, these coefficients are having their values equal to A11 is 0.5, A12 is 0, A13 is 1, A21 is 1.5, A22 is -1 and A23 is 1. Therefore, if we make use of these values and obtain a transfer function relating the mechanical power developed to the valve position. Now, this transfer function comes out to be a very simple transfer function of the form 1 minus STW that by 1 plus 0.5 STW. Now, let us understand what are the factors on which this water starting time or time constant TW depends upon. Now, this time constant TW is associated with, you can write TW, is associated with the acceleration time for water in the penstock between turbine inlet and forebay. Now, basically it represents the acceleration time. Now, the equation for this time constant TW is L into V divided by HT into G. Now, here L is the length of the penstock in feet, V is the velocity of the water in feet per second, HT is the head in feet and G here is the acceleration due to gravity. G here is acceleration due to gravity, its value is feet per second square, its units are like that. That is, if you put actually value of G, it comes out with 32.2 feet per second square, 32. Okay. Now, what we do is that there exists a relationship between the power developed and the various parameters of the system. Therefore, in this equation the velocity will be replaced by power and other terms. That is, the power generated is given by this equation V into HT into A into E divided by 11.8. Here P is the power in kilowatts, V is the velocity in feet per second, velocity of the water in the penstock, HT is the head, A is the cross sectional area of the penstock in feet square or square feet, and E is the combined efficiency of the generator and turbine, the total efficiency that by. Therefore, what we do is that from this equation we express the value of V in terms of power, head, A and E, and then substitute this value of the expression for V in this equation 24.2. When you make the substitution, we get the expression for water starting time constant TW equal to 0.366 PL divided by HT square A into E. Here the value of G has been substituted as 32.2. Now, this time constant TW is a very important parameter so far the model of the hydro turbine is concerned. The hydro turbine, the transfer function has some special characteristic, and we will discuss the special characteristic of this hydro turbine transfer function. The transfer function of the hydro turbine, which we have just now derived, is 1 plus TW S 1 plus 0.5 TW S. This is minus here. correct, thank you. This is minus 1 minus TWS, 1 plus 0.5 TW, okay. This is okay, is minus. Now, we can write down here mechanical power output Pm and the gate position Pgv. Now, this transfer function has one special characteristic, that is, if I look at the poles and zeros of this transfer function, then it has 1 0 in the right half of the S plane, and transfer functions or the systems which have at least 1 0 or 1 pole in the right half of the S plane are known as the non-minimum phase transfer functions or non-minimum phase systems. We shall analyze the special characteristic of this turbine, hydro turbine, by considering a unit step input to this turbine. That is, we change the valve position suddenly, and once we give a unit step input to this hydro turbine transfer function, right, then we can write down the expression for mechanical power developed. Now, here instead of considering the PGV, we will prefer to consider this deviations in the gate position, okay, and deviation in the mechanical power developed. Therefore, when I consider the deviations, I can write down the model in this form, that is delta PGV is the input and output is delta P. Okay. Now, when we consider the unit step change in the position of valve or gate of this hydro turbine, then delta PMS can be written as 1 by S 1 minus TWS over 1 plus 0.5 TWS. Okay, because we have considered the unit step change in gate position, so that the transfer function, not the transfer function, but the Laplace transform of unit step input is 1 by S. We shall write down this function in this form 1 by S take this TW out, so that we can write down here 1 by TW minus S divided by, take the 0.5 TW, so that you can write down 2 by TW, okay, plus S. That is, we are writing in the form S plus A, or here actually S minus A. This is numerator, directly it is not going to come actually in our expression for the response. This can be written as 2 by S 1 upon TW minus S divided by 2 by TW plus S. Okay. We obtain the time response by taking the inverse transform of this transfer function. That is, we can obtain delta PMT by taking the inverse transform, that is Laplace inverse of this whole function, which I can write down here as 2 by S 1 by T W minus S divided by 2 by T W plus S. Okay. Now, we obtained the partial fraction of this, and the partial fractions will come out to be like this. This will come out to be equal to Laplace transform of Laplace inverse of 1 by S minus 3 over 2 by T W plus S. That is, if you simplify this expression, you will get this expression. You can just check it. Okay. Now we can say that delta P M T is equal to 1 minus 3 e to the power minus 2 by T W into T. This is the response of the hydro turbine to step unit step change in valve position. Okay. Now, if I put t equal to 0, that is at time t equal to 0, that is delta P M O is how much? Is equal to minus 2. And if I put now t equal to infinity in this equation, I will get delta P M infinity equal to 1. Now, you can appreciate actually or the difference in the normal response which we get for a transfer function for a system. Suppose there is a system and we give it some input, we expect that the output should start following the input. Now, here we find that when at time t equal to 0, when I give a step change in valve position, then immediately the change in mechanical power is minus 2. We have given a unit step input, but the output is negative and it is as high as minus 2, and under steady state condition the output is same as input, right. Now, this is the main difference or main special characteristic of the hydro turbine. Now, if I plot the response here, that is time t delta P M, we start at minus 2, at t equal to 0 its value is minus 2, and it settles to value equal to 1, so, and it varies exponentially. So, that response is of this form. The time constant is T W by 2, right. That is, if you draw a tangent to this response curve at t equal to 0, then the curve will be this tangent will be like this, and this time can be identified as T W by 2. The meaning is that if the change in mechanical power changes at the initial rate, then it will reach its steady state value in time equal to T W by 2, right. Otherwise, it is varying exponentially. Now, to understand what is the implication of this special characteristic of the hydraulic turbine on the type of governor which will be required. Now, let us first consider that we use a simple governor, no special features, a simple governor, and let us see what will be the requirement for stable operation for this system. To understand this special requirement, let us start with the simple governor. We can represent the governor by a simple transfer function 1 by r. The transfer function of the hydro turbine or hydraulic turbine is 1 minus T W S 1 plus 0.5 T W S. Output of this hydro turbine will act on the inertia of the turbine generator system. There is 1 upon 2 H S. I am neglecting the damping term. This becomes my speed deviation delta omega r, and here is a negative feedback. Okay. This is negative, this is change in reference. This term is delta omega reference. I give us and is a plus. Now, to analyze the stability of this system, what we will do is we will consider the H equal to, say let us say H equal to 5. Okay. Let us take T W equal to, what was the T W taken 2. Okay. Now, with these parameters, we shall find out that what are the requirements on speed regulation parameter. Our basic requirement, it is a closed loop system, and this system should have a high degree of stability. It should have a required stability margin. To analyze this requirement, we write down the characteristic equation of this system. The characteristic equation can be written as 1 plus 1 by r 1 minus T W S over 1 plus 0.5 T W S into 1 upon 2 H S. Now, here this is the forward loop transfer function 1 by r into this transfer function into this. This is the forward loop transfer function, and the feedback is unity feedback, and the characteristic equation is 1 plus G H, which is the standard formula, and it comes out to be equal like this 1 plus 1 by r like this. Now, let us substitute the value of T W equal to 2 and H equal to 10, and let us see 1 plus 1 by r 1 minus 2 S 1 plus S 1 by 10 S. Okay. We can write this as 10 S R plus is it okay? Or we can write this in the form now 10 R S square plus 10 R minus 2 into S plus 1 equal to 0. Therefore, this is a second order characteristic equation, and for this second order characteristic equation to have its roots to lie in the left half of the S plane, our requirement is that these coefficients should be positive. Therefore, from this consideration that these coefficients should be positive, one requirement is now that 10 R should be greater than 0, or we can say R should be greater than 0. The second requirement here is that 10 R minus 2 should be greater than 0. This puts the requirement that R should be greater than 0.2. It means from the consideration of stability, the minimum value of R which we can choose for this governor is 20%. Generally, the speed drop which we choose, or the governor parameter or drop parameter of the governor is taken around 5%. Now, if I take the R equal to 5%, then this system is going to become unstable. Okay. Now, suppose I want actually the response to be critically damped, then for critically damped response, our requirement is 10 R minus 2 whole square minus 10 for 40 R equal to 0. Okay. That is B square minus 4 AC should be equal to G2. Now, if you solve this equation, the value of R which is required comes out to be 0.736, and another value of R is 0.05. What is the value? 536. Okay. It means we get two roots of this equation. One root says that the value of R, if I call it R1, call this as R2. One root says it should be R should be 0.736. The meaning of 0.736 means it is a 73.6%, right? And when I say R2 equal to 0.0536, it is 5.36%. But if you assume R2 equal to 0.0536, then it does not meet this requirement that R is greater than 0.2. And if you take this value of R equal to 0.0536, this will come out, or this will result into a damping ratio equal to -1, that is negative damping. And with R1 equal to 0.736, it will have a critically damped response where zeta will be equal to 1, right, but this is too high. And therefore, in order to overcome this problem, the hydro governors which are provided have to have different characteristics. Now, we will discuss the characteristic of the hydro governor which is required for hydro turbines. Now, this is the block diagram of a hydro governor, that is the governor for hydraulic turbine. The building blocks of this governor or speed control mechanism or the hydro governor is similar to that we use in steam turbine. The only difference which we will see here is that this block dashpot. Okay. Now, let us just discuss what are the main blocks. The first block we can see here is the speed governor. The speed governor senses the speed and it gives you a position which is proportional to the speed deviation or speed, right, that is the speed governor position. This first block, pilot valve and servo motor. The input signal to this pilot valve and servo motor are the speed governor speed changer position, which is the signal which comes from AGC of the system, and another is the position of the governor or speed governor position. These two are the input signal to the pilot valve and servo motor. The output of this pilot valve and servo motor goes to another servo motor, hydraulic servo motor, which is named as distributor valves and gate servo motor. Now, these two servo motors are required to amplify the power which is required to move the gates, and the output of this hydraulic servo motor controls the governor control valves or gates of the hydraulic turbine, and the output is the gate position. Okay. Now, this dashboard is to provide a feedback signal, and this feedback is a derivative feedback. This dashboard is to realize a derivative feedback. Then you can see here actually that there are two input signals coming. One is directly coming from the position of the servo motor, another is coming through dashboard, right. Now, these two feedback signals are required to obtain the required characteristic for the hydro governor. Now, this shows this block diagram shows the transfer function of various building blocks of the hydro turbine governor or hydraulic turbine governor. We start like this. This is the transfer function of the pilot valve and servo motor. This is the time constant of the distributor valve and servo motor. TG stands for time constant of the distributor valve and servo motor. Here we show the rate limits. Then this transfer function 1 by S to represent the integration function, and another limits which we have is the position limit, right. Therefore, these two limits are shown in this transfer function diagram, and whenever we are studying the small perturbation dynamics or whenever the system is subject to the small perturbation, then these limits particularly may not be touched. Particularly the position limit may not touch, but the rate limits may have to be incorporated. Again, you can see here there exists a non-linear function to relate the gate position to the hydraulic servo motor position. That is, when the hydraulic servo motor piston moves, right, it moves the gates, and the movement of gates and the movement of the servo motor, they are again related by a non-linear function. Therefore, this shows the non-linear function. The transfer function of the dashpot is delta STR over 1 plus STR. Now, this transfer function, you can see here that it is a derivative feedback. It is a derivative feedback because we have a term S in the numerator, that is STR over 1 plus STR. This becomes a derivative feedback. Then this term delta is called tangent droop. Delta is called tangent droop. Then the another feedback which was shown in the block diagram is through this sigma. Now, this sigma is same as R which we use actually in the models for the for the governors. Now, this sigma is known as the permanent droop. Permanent droop. The meaning here is that when the system is in dynamic condition, right, there will be output from the dashboard, and the moment the system attains the steady state condition, right, there will be no output signal from this transfer function, and therefore the net droop will be determined by the permanent droop sigma only. Okay. The typical parameters of this hydro governor are this TR is 5 seconds. It ranges in the range of 2.5 to 25, a wide range. TG is the time constant of the distribution valve and servo motor. This time constant is small and its value is 0.2 second and its range is 0.2 to 0.4. The TP, which is the time constant of the pilot valve and servo motor, this time constant is very small, of the order of 0.04 second, and it is in the range of 0.03 to 0.05 second. The delta, the temporary droop, its value is 0.3 and its range is 0.2 to 1. The sigma or R, its range is, its value is 0.05 and it varies from 0.03 to 0.06%. Normally it is 5% permanent droop is considered, and some places it may be lower than this or slightly higher than this. Its range is very narrow, it is 0.03 to 0.06. Further, this time constant TR is depends upon the water starting time constant, right. Therefore, the typical value is that TR should be equal to 5 times TW. This is a thumb rule. Okay. And suppose if TW is 1, then TR is 5. Suppose TW is 2, TR becomes 10, and so on. Similarly, this temporary droop is 2.5 TW divided by 2H. Therefore, you can say that the temporary droop requirement depends upon the inertia constant of the turbine generator system and the water starting time, right, because as we discussed actually that this special feature that we have to provide a temporary droop compensation, right, particularly to take care of special characteristic of the hydraulic turbine, and there is a relationship which relates temporary droop to water starting time constant TW and inertia constant H. Now, the question arises that how do we optimize the parameters of this hydro governor? One way is that okay, you take this thumb rules, that is you set the value of delta as given here in the range of 0.3, around 0.3, 0.2 to 1, or use this formula, delta is 2.5 TW divided by 2H. For example, in this case when I put TW equal to 1 and H is taken as 5, how much it comes out to be? 0.25, 0.3 is one what we are talking about. But however, in any particular system, the procedure is that you model the complete system, like the hydro turbine. take the its associated governor, right, and you obtain the dynamic response of this system, and we can use different techniques to set the parameters of these governors, right. Generally the governor parameters are set under no load conditions. The general model for speed governing system is developed, and this is shown in a compact transfer function like this, where input is delta omega, the speed deviation signal, and the transfer function is in the form k into 1 plus s T2 divided by 1 plus s times T1 or 1 plus s times T3. The output of this transfer function represents the change in power delta P. Now, this is added to the reference setting, that is PO, which is the reference setting, and this output, which is the sum of PO and delta P, right, is the gate valve or gate valve position. Okay. Now, here as you know actually that this PO is the position of the speed changer. In the AGC, when we talk about this is the speed changer position. Now, these time constants T1, T2, T3, right, these time constants are can be obtained from the typical values which are given here for this Tp, Tr, delta, sigma and Tg, so on. That is, these time constants T1, T2, T1, T2 and T3, right, are related to the parameters of this governor, okay, and this is put in the simplified form for the purpose of simulation studies. Okay. Now, another important point which we have to see here is that there are different manufacturers of hydraulic governors. There are hydraulic governors have been manufactured by the General Electric Company, by Westinghouse and so on, right, and therefore, these manufacturers give the parameters of the model of the governors developed by them, right. Therefore, the standard references are available where the parameters of different manufacturers are given. If you look into the reference material which I have given to you last time, that is the IEEE committee report, right. Then in this report the parameters of different types of hydro governors are given. Now, these parameters are generally the typical values. However, for any utility has to set its own parameters by performing certain studies. Now, as we have studied actually that the excitation system and automatic voltage regulator parameters need to be set. Similarly, the parameters of the governors need be set, because so far actually the turbine parameters are concerned, they are constant. Only flexibility which we have is actually in setting the parameters of the hydro governors for hydro turbine and other governor for the steam turbine. Now, this constant K which I have shown here, this K is the gain of the governor. This gain is basically the reciprocal of the permanent droop, that is R. If R is taken as 5%, the gain will become 20, right, and the standard techniques which are used for setting the parameters are either by time domain simulation or by frequency response analysis. Okay. Let me sum up that we have studied the dynamic model for the hydro turbine. We have also seen the special characteristic of the hydro turbine transfer function, and to meet the requirement of the hydro turbine, the hydro governor is required to have a special feature, and that feature is to have a temporary droop concept. Now, when this hydro governor with the temporary droop is provided and if the parameters are properly set, it will give the desired dynamic response for the system. Thank you.